will give you an idea of the most important points. Of course, the presentation will be based on my work, but I will also be enriching it with some details that I had the chance to learn this summer at Brown University in the US. To begin with, this project was completed in the framework of the Middle Years program. It is a quinquennial international educational program that my school follows. At the end of it, each student is given the chance to conduct research, create a product, evaluate it, and submit a report on a topic of their choice. I selected Heisenberg's uncertainty principle, a fundamental concept in quantum mechanics which governs the very, very small things in our universe. My project is a 20-page document, and it sure is the outcome of research, but not just that. As I am sure many of you are, I too am interested in understanding how the universe functions and why it functions the way it does. So, how can we know? The answer is physics. And what is one of the most fundamental fields of physics studying this? Quantum mechanics. And then you say, perfect, quantum mechanics, and you get excited and you start exploring it and it's great, until these show up. And as my instructor at Brown, Dr. Umberto Gilmer, pointed out, you might then start questioning your knowledge. You understand what is missing. And you might even end up wondering about people, but let's not be too dramatic. In a less extreme scenario, someone seeing this math might just stop bothering with the topic. Especially for students of our age, only having a knowledge of high school physics, it is particularly difficult to find books and papers both explaining advanced concepts and considering our level of knowledge. I'm sure many students are interested in understanding the physics of our universe. Some of them devote more time, they read, they encounter unknown concepts, they look them up, then other unknown concepts pop up, and they end up with loads and loads of tabs open in their computer. And somehow, they now have more questions than when they started, but at least they acquire better understanding. However, this is not the case for everyone. That is why I decided to create a document introducing in a precise and entertaining manner one of those advanced concepts, Heisenberg's uncertainty principle. Not only to help others understand as if I already knew, but also to help myself better understand, because I too was struggling. High school students are the main intended readers, yet anybody having similar knowledge of math and physics might want to read it. So, I've introduced a project about Heisenberg's uncertainty principle. But what is that? I think it's time to really get to know both that and what that document includes. Of course, I won't have the time to explain in detail everything that is included, but I will give you an idea of the most important points. Heisenberg's uncertainty principle was formulated in 1927 by German physicist Werner Heisenberg. It expresses a relationship between two measurable quantities, A and B. The important thing about those quantities is that they do not commute. What that means? It means that the order in which they are multiplied matters. A times B is not equal to B times A. In this case, we can define a quantity called a commutator. A commutator of A and B is equal to A times B minus B times A. And as you can see, if A and B commute, their commutator is zero. If A and B do not commute, their commutator is non-zero. There are several quantities which do not commute and for which the principle can be expressed. The most common ones are position and momentum. Remember that momentum is the product of mass times velocity. So let's move on to the definition. According to Heisenberg's uncertainty principle for position and momentum, exact values cannot be assigned to the position and momentum of a system simultaneously. These quantities can only be determined with some uncertainty. The greater the uncertainty for one quantity, the less the uncertainty for the other. And here, it is important to note that the uncertainty cannot be zero. The explanation for that is quite straightforward. We will only need to consider the general form of Heisenberg's uncertainty principle for position and momentum, which is this. Delta x and delta p represent the uncertainty in position and momentum respectively. Psi represents the state of the system, and between the two psi's you can see the commutator of x and p. Since position and momentum do not commute as we saw before, then their commutator is non-zero, which is why the second part of the inequality is non-zero too. And because it is also positive, as we will see later, delta x and delta p cannot be zero. You can also see the simplified version of the same inequality, where h is Planck's constant, a really small number approximately equal to 6.6 times 10 to the negative 34 joules times seconds. And here you understand why the second part is always positive. But is there a way to better perceive uncertainty and understand it? The answer is yes. There are different ways to approach this. Today, I will elaborate on wave-particle duality and wave functions. Let's begin with wave-particle duality. According to it, a particle can behave both like a particle and like a wave, which to us might seem strange, but it is true. As in the double-slit experiment, the wave-like behavior of a particle can only be observed after many measurements, and the wave-like pattern that is created shows the probability distribution for the position of the electron. In other words, it shows the likelihood of the electron having each value of position. So we understand that this wave is not a physical wave like a mechanical wave. It is rather a mathematical object. Specifically, it is derived from the so-called wave function of a system. The wave function is a mathematical wave too, and it describes the state of a system, such as what position it may have or its energy level. It is usually symbolized using the Greek letters psi or phi, and it has a general form which can be expressed using different bases. This way of expressing it is particularly useful when dealing with measurements. The most common bases are position bases and momentum bases, psi of x and psi of p respectively. Here, it is important to clarify that being at the position basis, for instance, doesn't mean that we can only examine position. We can examine momentum too, or some other quantity. The only difference is that we will have to express it in terms of position. To better understand this, imagine that the different bases are different languages that express the same wave function, like the same idea. So the only difference is the code used to do this. Returning back to what I was saying before, wave functions do describe the state of a system, but they are neither what we can measure nor what we see in the double-slit experiment. What we can measure is the probability distribution, which is given by squaring the magnitude of a wave function. And now that we have this new relationship, we can create the respective graphs. Here are some simplified versions using the position basis just to better understand uncertainty. The trick here is that whenever you see a peak, you understand that the value of position is most probably somewhere around the peak. What about momentum? We will have to use the Brohl hypothesis for that. It relates wavelength to momentum. So let's examine the first case. Even though the curve is quite large, we understand that there is a peak around the middle, which is why the uncertainty in position is not very large. But because there's only one curve and we cannot know the wavelength of this wave, the uncertainty in momentum is large. In the second case, there are many peaks of equal height, so we cannot know which is the most probable value for position. That's why the uncertainty in position is large. But because the wavelength is quite clear, the uncertainty in momentum is small. After having said all that, I'm sure there must be people thinking, all right, you've talked about Heisenberg's uncertainty principle. So what? Are there any applications? There sure are. And one of them relates to the Bohr model, the atomic model that Bohr introduced and looks like this. I'm sure most of you are familiar with it. According to the Bohr model, the atom consists of a positive core and electrons traveling around it at fixed distances. But even though this model is still used in some cases, it doesn't always depict reality, and we can use Heisenberg's uncertainty principle to show why. The problem with the Bohr model is that it suggests that we can know the exact position of the electron in terms of distance from the nucleus, and this violates Heisenberg's uncertainty principle. Using the principles inequality, we can find the minimum uncertainty in position for the electron, which you can see on the board. This uncertainty for position is greater than the diameter that the Bohr model suggests, the diameter of the atom. This doesn't only mean that the electron could be found outside the atom that the Bohr model suggests, it also means that it could be found somewhere between those fixed orbits. And that is why the Bohr model is inaccurate. In reality, the atom looks more like this. Actually, this is not exactly reality. It is a depiction of the possible positions that an electron could have in a specific state of the atom. In other words, it shows the probability distribution for position of the electron, and it is called an electron cloud. But since an atom can be in many different states, here is a more detailed depiction of the electron's position probability distribution clouds for the different states of the hydrogen atom. Now, remember I told you that all this is presented in an entertaining and friendly manner? That's because it is all written as a fun journey, where the reader has several friends who are athletes and provide real-life comparisons whenever possible. So I would like to end my presentation by reading you some extracts from the beginning and the end of my project to show you how that works. The quantum world. Think of everyday life. Imagine you were a skillful basketball player and you were about to shoot. You calculate the angle with which you will throw the ball and you are sure that you will make it. Everything seems perfect until a gust of wind blows the ball and you miss. You may be annoyed, but you're definitely not scared. This could have happened to any athlete performing ball sports. Nothing was strange, you just didn't consider all the variables. Otherwise, you would have predicted the path that the ball would follow. That seems rather straightforward, right? And it is, in the classical world, in the microscopic world where humans live. But you cannot say the same thing about the quantum world. Boom! Now everything becomes confusing. What do you mean I can't know which path the ball would follow? Keep calm. We will make this clear. And after making this clear, we end up here. Throughout our journey, did you ever wonder if the uncertainty principle is just a concept in quantum mechanics? Of course no, we would all say. All the time we were squeezing our brains to understand all that stuff. And it's true. So we can think about it now. Even though Heisenberg refers to a principle applicable on a scale which we do not perceive, we may draw conclusions about our life as well. Tennis player. Hey, we're here too. Stop philosophizing. I can't stand thinking about uncertainty anymore. Wait a second. Is it maybe this uncertainty that is stressing out athletes? Is it something different? Maybe for them, whatever is true about the world and can affect their performance matters, even if it is not perceivable in macroscopy. We may never know. However, a lot of them will most probably keep their rituals to concentrate and ensure that everything will go as planned. In this picture, you can see Rafael Nadal, one of the greatest tennis players, arranging his bottles, and he states, "This way, I make them the same each time so I can concentrate solely on the game and what lies ahead." Thank you very much.
Congratulations, Marina, for your great presentation and your accuracy.